As a part of polynomials, in the last class we discussed about synthetic division. Synthetic division or Horner's process for linear factor as well as for quadratic factor. That was we discussed in the previous class. And before that, I mentioned you about division algorithm of polynomials and the way of division. Okay. So division algorithm of polynomials or division process or synthetic division process, these three, okay, usually helps us to find quotient polynomial and remainder polynomial when a given dividend polynomial is divided by a given divisor polynomial. Okay, so we usually use any one of the process like either usual division or synthetic division to find remainder and quotient. And specifically now in this class we are going to discuss about remainder theorem and factor theorem, right? So whenever this remainder theorem and factor theorem helps us. See, remainder theorem helps us to find reminders easily if divisor is linear. Okay, whereas factor theorem helps us to find linear factors easily. Specifically here I am mentioning that here the divisor is linear as well as here we are finding linear factors. So that in turn represents that remainder theorem and factor theorem are helpful if the divisor or the factor is linear. If it is not linear, if it is of any other degree other than 1, then you need to go with the division algorithm of polynomials. Division algorithm of polynomials helps us to find remainders of any degree, divisors of any degree, but that is applicable for divisors of any degree, but these two are applicable only if the divisor is of linear and see maybe the factors is of linear. Factor and divisor just both are same, right? So what this remainder theorem says, okay? First of all, what this remainder theorem says, and then I will discuss about factor theorem. Okay, a remainder theorem. This remainder theorem states that basically, if a polynomial f of x is divided by x minus a, then remainder is f of a. So without going with the actual division, directly f of a is the remainder. That is just a statement from the remainder theorem. So once if you look, if I have a polynomial f of x, if I divide this polynomial with x minus a, okay, I don't know about the quotient polynomial as well as the remainder polynomial. For suppose you just take q of x is the quotient polynomial and r of x is the remainder polynomial. Okay, but one thing is very clear, here the divisor is linear of 1 degree, linear in the sense 1 degree. Since the divisor is linear of 1 degree, as we know, remainder is always less than divisor degree. Degree of remainder is less than degree of divisor. Since it is of degree 1, it should be of degree which is less than 1, then for sure it is of degree 0, which in turn represents that a constant r. So the remainder is a constant polynomial. So now when you apply statement of division algorithm for this division, dividend from this, okay, we have dividend f of x is equals to divisor x minus a into quotient q of x plus remainder r. That remainder is just a constant polynomial, so use constant r. Now our target is to find remainder, so I need to find remainder using this f of x. I don't know about quotient. To eliminate this quotient, I will make this x minus a as 0. This is the statement of division algorithm which is true for all the values of x. So you may take any value in the place of x for this. So take x is equals to a. My intention is to eliminate q of x. So take x is equals to a. If you take x is equals to a, what will happen? this f of x will become f of a is equals to a minus a into q of a plus the constant polynomial, or the constant is r. This a minus a is 0, 0 into anything is 0, then we will conclude that f of a is equals to r. And finally, that r is simply reminder, that reminder is f of a. That in the sense, you will get reminder when f of x is divided by x minus a just by replacing x with a in the polynomial. F of a means what? F of a is the polynomial value when you replace x with a. That polynomial value directly represents the remainder. So remainder theorem helps us to find remainder easily. But about quotient, remainder theorem won't say anything about the quotient. Okay, so to find quotient and remainder both, then you need to go with synthetic division. Okay, so to find quotient and remainder both easily, you just move with the synthetic division as we discussed in the previous class. But if the question asks you to find only remainder, then no need to move with the division, no need to move with the synthetic division. Directly you will get remainder just by replacing x with a. That polynomial value f of a directly represents remainder. Okay, once again I will explain for you the statement. Okay, I have a polynomial f of x and we are dividing that polynomial with the linear factor x minus a. Then the remainder obtained in that situation is what? F of a. That's it. Okay, just have a look. So just look at the board. I have two simple problems to find the remainder using remainder theorem. Just look at the first one. See, x power 4 minus 3x cube plus 7x square minus 8. If you divide this particular fourth degree polynomial with the linear x minus 2, what is the remainder? That's my question. See, finding remainder, if you go with the actual division process, since it is of fourth degree, this is of first degree, you need to go step by step in 4 steps to find the remainder. But it is bit lengthy. So, to find the remainder easily, either you may use remainder theorem or you may use synthetic division also. That synthetic division process also is somewhat simple only. Okay, but here we need only remainder, not quotient. So, remainder theorem is enough. Our target is to find the remainder, and this is the polynomial. As per the situation, this question mark, remainder is simply nothing but f of 2. If you treat this polynomial, dividend polynomial as f of x, and since the divisor is x minus 2, functional value f of 2, just replacing x with 2 directly gives you the remainder. F of 2 is equals to 2 power 4 minus 3 into 2 cube plus 7 into 2 square minus 8. So just try to simplify it. This is equals to 16, 2 cube is 8 3 is 24, plus 4 7 is 28 minus 8. So we need to simplify. 28 minus 8 is 20. 16 minus 24 is minus 8. 20 minus 8 is 12. And this 12 is the remainder. Simply just by using remainder theorem, just one simple simplification that gives you 12 as the remainder. Okay. If you wish to check, just go with the usual division and check it. You will get remainder as 12. Okay. That's it. Now the second problem. Just look at this dividend polynomial. This dividend polynomial is of 2020th degree, whereas the divisor is of linear first degree. So finding remainder by dividing this 2020th degree polynomial with this x plus 1 needs actually 2020 steps of division if you move with the actual division. Okay, so doing division with it in 2020 steps is very complicated, but remainder theorem avoids all that complication and directly gives you the remainder. As per our discussion, here the remainder is simply nothing but f of minus 1. You may say f of minus 1 or p of minus 1, anything. Polynomial, you just give one name for the polynomial. Just I am treating f of x as the polynomial, or may some people treat it like p of x. So then you just consider it as p of minus 1. So p of minus 1 is what? Polynomial value by replacing x with that minus 1. So this is equals to 7 into minus 1 power 2020 minus 5 into minus 1 power 1000 plus 17 into minus 1 square minus 1. So this simplification directly gives you the remainder. Minus 1 to the power even number is 1. So 7. Minus 1 to the power even number is 1. So minus 5. Minus 1 square is again 1. So directly plus 17 minus 1. So when you observe 5 and 1 is 6, 7 minus 6 is 1, 1 plus 17 is 18. So when you divide this particular dividend polynomial with the divisor x plus 1 at the end, you left with the remainder 18. So here in this case remainder is 18, here in this case remainder is 12. So remainder theorem directly gives us the remainder. Okay, but remainder theorem won't help us to find quotient. If you need quotient also, then instead of division, you just go with synthetic division. That's other thing, and I will give you some problems related to that in the next point. Okay, first of all, you just pay attention on the remainder theorem. So simply, remainder is simply equals to f of a or p of a. That's the remainder theorem. Have a look. So if I have a polynomial p of x, if you divide that particular polynomial p of x with x minus k, then the remainder is simply the functional value when you replace x with k. Then the remainder is what? P of k. When we divide polynomial p of x with x plus 4, then the functional value is simply nothing but p of minus 4, and that p of minus 4 is the remainder. If you divide that p of x with x, x can be written as x minus 0 or x plus 0, you just replace x with 0, directly p of 0 is the remainder. And if the polynomial is p of x and we are dividing that with ax plus b, so think about that ax plus b, then the remainder is simply nothing but you need to replace x with this 0 of divisor, ax plus b. What is the 0? Minus b by a. So just replace here, then the divisor is simply nothing but p of minus b by a. Simply if I say have something like a 7x minus 8, then what to say about the remainder? You just replace x with 8 by 7. So that p of 8 by 7 will represent the remainder, right? So these are the polynomial values at these points k, minus 4, 0 like that, and these values, polynomial values directly will represent the reminders. Okay, this is something about the reminders, and we have different problems to solve, and I will discuss one by one. And before that, we need to learn factor theorem. Okay, so have a look. After that reminder theorem, we need to discuss about factor theorem. Factor theorem is basically useful to find factors, okay, to decide whether the divisor is an exact factor or not. And the theorem states that if f of x is a polynomial such that f of a is equals to 0, then we will confirm that x minus a is a factor. See, to mention anything like x minus a or is a factor for the polynomial, see, this is mentioned as a factor if the remainder is 0. What I am saying is, as we discussed in the previous class, when you divide f of x with a polynomial g of x, and if the remainder is 0, then that g of x is mentioned as the factor for f of x. But here we are trying to decide whether x minus a is a factor or not. So for that, what you need to do? You just divide the polynomial f of x with x minus a. When you divide f of x with x minus a, you will get some remainder, right? So when you divide f of x with x minus a, you will get some remainder. But according to the remainder theorem, since we are dividing with x minus a, we know that the remainder is simply nothing but f of a. When you divide f of x with x minus a, the remainder is f of a. Given f of a is 0. Since f of a is 0 in the statement, so remainder is 0. Since remainder is 0, the division is exact, and we call that x minus a is a factor of f of x. So simply if the remainder, see, to find the remainder from remainder theorem, that the remainder is f of a, but in factor theorem, to decide the factor, you need to check whether f of a is equals to 0 or not. If f of a is equals to 0, then the linear factor of the polynomial is simply nothing but x minus a. Okay, so x minus a is a factor of f of x. This is basically the statement of factor theorem. Okay, so if we have a factor for a polynomial, then the functional value is directly what? 0. So I will erase it and I will discuss something. Just I will look basically factor theorem. Once again I state for you, if f of x is a polynomial such that f of a is equals to 0, then x minus a is a factor. Just it's an application of the reminder theorem. Okay, but based on this factor theorem we will solve different problems. Okay, I will give you. Just have a look. E. So what we need to mention? See, x plus 3 is a factor. X plus 3 is a factor of a polynomial, say some p of x. Since x plus 3 is a factor of p of x, it represents that the remainder is 0. Remainder is 0 in the sense, what is the remainder actually? P of minus 3. So p of minus 3 is equals to 0. That's one part. And the other way, see, for suppose you may take f of 7 is equals to 0, then factor of f of x is, as per the factor theorem, since f of 7 is 0, so the functional value at 7 is 0, that in turn represents that x minus 7 is a factor. Then factor of f of x is x minus 7. And for suppose if I have anything like g of minus 1 is equals to 0, then since g of minus 1 is equals to 0, then x plus 1 is factor for g of x. Is it right? Since x plus 1 is factor for g of x, that implies we have a chance to write g of x as g of x is equals to x plus 1 into some quotient. This way of representation is also helpful. Just think about it. If it is a factor, the functional value is 0. If the functional value is 0, then it will become a factor. If this is a factor, then you have a chance to write in this format. Have a look, this is something about factor theorem. Okay? So look at the code, one simple problem. X plus 1 and x minus 3, if they are factors of this polynomial, then you need to think about p comma q. See, just look there. X plus 1 is a factor. Since x plus 1 is a factor of this polynomial, the functional value is 0. So for suppose if you treat the polynomial as some f of x, since x plus 1 is a factor, from factor theorem we are very clear that f of minus 1 is 0. So replacing x with minus 1, that implies minus 1 to the power 4 minus 2 into minus 1 to the power 3 plus p into minus 1 plus q is equals to 0. Why it is equals to 0? Because x plus 1 is a factor. So minus 1 to the power 1 is 1. Minus 1 power 3 is minus 1, minus of minus plus 2. Minus p plus q is equals to 0. So from there, q minus p is equals to minus 3. We have one relation between q and p. Okay? And not only this x plus 1, x minus 3 is also a factor. Again, from factor theorem we are clear that f of 3 is equals to 0. Because x minus 3 is a factor, replace x with 3, that give you, that is 0. So replacing x with 3, 3 power 4 minus 2 into 3 cube plus p into 3 plus q is equals to 0. Just try to simplify. 3 power 4 is 81, 3 cube is 27, 27 into 2 is 54. So 81 minus 54 we need to simplify. So 3p plus q is equals to, this is 81 minus 54. So how it becomes? 6. Maybe 27, right? 54 and 27. So 81 minus 54, when you set it that side, it becomes minus 27. So q minus p is minus 3. 3p plus q is minus 27. Use these two to find the values of q as well as p. How to do? Just do subtraction or you just go with addition like that. Okay? This is q minus p, that is 3p plus q. Just think about it. What are the values of p and q from these two? Okay? I do one thing. I just directly subtract. This is q minus p minus 3p minus q. q minus p minus 3p minus 2. Q and q will get cancelled. You will be left with minus 4p. And since we are subtracting minus 3 minus of minus plus 27. 27 minus 3 is 24. So p is equals to minus 6. Since p is equals to minus 6, what you say about the value of q? Replace here p with minus 6. Minus of minus plus 6. Send that 6 that side. Q will become minus 9. So at the end we have the values of p and q simply by solving these two. And these two are, since x plus 1 and x minus 3 are factors of that polynomial. Have a look. Suppose if we have a polynomial and a general nth degree polynomial in one variable, a n x power n, a n minus 1 x power n minus 1 and so on, a2 x square plus a1 x plus a0. Just have a look, this is a polynomial of nth degree in one variable x and all these are the coefficients. And now for this polynomial, if x minus 1 is a factor, what we need to say? Since x minus 1 is a factor, according to factor theorem, p of 1 is equals to 0. And since p of 1 is equals to 0, you just replace x with 1. So if you replace x with 1, what will happen? If you replace x with 1, a n into some 1 power n. So a n plus a n minus 1 plus a n minus 2 plus and so on plus, since we are replacing x with 1, a2 plus a1 plus a0 and that is equals to 0. So an plus an minus 1 plus an minus 2 plus and so on and plus a0 is equals to 0. Okay, and that implies, since sum of all these things is 0, what are all these things? They are simply sum of coefficients of p of x. Sum of coefficients of the polynomials p of x is 0. So if x minus 1 is a factor, p of 1 is 0. If you replace x with 1, sum of coefficients will become 0. So this is an if and only if condition. If x minus 1 is a factor, sum of coefficients of the polynomial is 0. If sum of coefficients of the polynomial is 0, then this will happen. From there, p of 1 is equals to 0. If p of 1 is equals to 0, x minus 1 is a factor. If it happens, we need to move in this way. If sum of coefficients is 0, we need to move in such a way. So always to decide whether x minus 1 is a factor for the given polynomial or not, you need to think about the sum of coefficients. If sum of coefficients is 0, then directly you have a chance to confirm that x minus 1 is a factor. And the next thing, if x plus 1 is a factor. See, if x plus 1 is a factor, then p of minus 1 is equals to 0. X plus 1 is a factor, okay? P of minus 1 is equals to 0. And if p of minus 1 is equals to 0, what will happen? Okay? P of minus 1 is equals to 0, you need to replace x with minus 1. Since we are replacing x with minus 1, so minus 1 to the power n, actually we don't know whether it is even or not. And that's why you just start from this direction. So a0, replace x with minus 1, minus a1, replace x with minus 1, plus a2, minus a3, plus and so on. We need to continue up to the last term. Okay? So this is equals to 0. So this is equals to 0 in the sense, what will happen? So just you rewrite it like this, a0 plus a2 plus a4 plus and so on is equals to a1 plus a2 plus, not a2, a3, a1 plus a3 plus a5 plus and so on. Just you observe, if x plus 1 is a factor, this a0 plus a2 plus a4 and so on is equals to a1 plus a3 plus a5 plus and so on. So these are nothing but sum of the coefficients of the even powers, and these are the sum of the coefficients of the odd powers. So if x plus 1 is a factor, then p of minus 1 is equals to 0. That in turn represents that sum of the coefficients of the even powers is equals to sum of the coefficients of the odd powers. This is also an if and only action. Okay. If sum of the coefficients of even powers is equals to sum of the coefficients of odd powers, then this is correct. P of minus 1 is equals to 0 is correct. And so we say that x plus 1 is a factor. So deciding x minus 1 or x plus 1 as a factors or not is somewhat simple. Directly you need to check these two, or you need to think about sum of the coefficients, or sum of the even coefficients is equals to the sum of the coefficients of odd powers. Just have it. Okay. And the next thing is this very simple one. X is a factor. See, since x is a factor, as we discussed earlier, you just express that x as x minus 0 or x plus 0. Since x is a factor, we need to take that p of 0 is equals to 0. So p of 0 is equals to 0. So p of 0 in the sense replace x with 0. If you replace x with 0, everything will become 0 except that a naught. So p of 0 is equals to 0 in the sense a naught is equals to 0. What is that a naught? That a naught is the constant term of the polynomial. If that constant term of the polynomial is 0, if a naught is 0, p of 0 is 0 and x is a factor. So if x is a factor, constant term is 0. That in the sense no constant term in the polynomial. If there is no constant term, that means constant term is 0, which gives us x as a factor. So x minus 1, x plus 1, x, these are some special linear factors. If they are factors for the given polynomial, these conditions will happen. Okay, have a look.